Plasma technology offers both plasma-based technology and ion beam-based technology. And today our plasma technology is really based around inductively coupled plasmas, or ICPs as we call them. Ion beam's pretty much as it was since it was initially created, so ion beam etch and deposition. But ICP is known to be a low damage type process, so it means that we can create devices that are sensitive to plasmas much more routinely or safely. Initially, when plasma was formed, it was based around a technology called reactive ion etch, and the difference between that is that there's only one source there that can create the plasma. But reactive ion etch has been around since the beginning of the company, and that's what we still use today. So if you went down onto our shop floor, you would still see 80 systems down there, or 800 systems on the shop floor, and they've really been around since the start of the business. They've grown up through the business and they've been developed in terms of how they might be controlled and the processes that they offer, but generally they've been around since the start of the company. In terms of those that have evolved, I would say it's more how we create the plasma. So it's not so much that they've come and gone. We've either developed them, enhanced them, improved them. What we found is that as the industry changes in wafer size, so when it was first founded it started on 2-inch substrates. We're now mainstream's up to 450 millimeter, so much larger substrates. So generally where we've changed is in the source size. So initially it was for smaller wafer formats, which would be our ICP 65 if we were to talk about inductively coupled plasmas. But we now have sources that are compatible across a 450 millimeter area, so they're much, much larger in dimension. And it's really all about how we manage to create that plasma to cope with the larger wafer formats. That's really how we've evolved with time, not so much that we've seen products disappear and come back, because we still have customers in the research environment that work on 2-inch substrates where it doesn't make any sense for them to take up all their lab space with a machine designed for a much, much larger wafer format. So we would still sell the smaller type systems to those customers. In terms of deposition, you have various methods of putting material onto wafers. You have what's known as CVD, which is chemical vapor deposition, and that's pretty standard in terms of exposing gases to the wafer. But what we have here is plasma enhanced chemical vapor deposition, where we introduce gases to the chamber, and through having plasma there, it helps improve both reaction and the deposition rate that we can achieve, and also the temperature that we can achieve it at. PECVD is pretty standard across most of the industry. It's for doing quite thick films. But what we've found is that by actually improving how we do our PECVD, so we start to introduce what we talked about a few minutes ago, the ICP element to that, we've now got what we call ICP PECVD. And there we can actually deposit much denser films and get the same type of properties that you would in, say, oxides or nitrides, but with a much thinner layer, which ultimately improves the device performance and throughput for the customers in their factories. Just about a year ago we launched Australis to the market. Australis was designed to be a deep silicon etch system, which is predominantly used in the MEMS market, so used for micro electromechanical systems. We also found that as a business we had a core technology or a core requirement from our customers to etch nanostructures, so nano electromechanical systems, so devices in the really tiny structures. With Australis we had to make sure that it could do the larger structures, so MEMS, and also NEMS at the same time. What that meant was the source had to be able to etch at reasonable rates, so we typically quote greater than 20-25 microns per minute, but then also etch very tiny structures. And it's that flexibility built into Australis that makes it a unique tool for the market today. With that system, it takes Oxford Instruments into a very competitive landscape, but it's really building on the 20 years that we've been playing in the MEMS market, and all that knowledge that we've gathered has gone into that particular product. So Oxford Instruments are continually investing in new technologies and developments. This year's no different. So this year we'll see the introduction of 2 new products in the next month or so, each geared towards the high brightness LED market sector. In that market sector, they're really driven by the cost per die, or dollars per lumen as they talk about in that sector, which means that as a business we're continually being driven to make sure our systems are giving them high throughput and low cost of ownership. The 2 systems that are coming through, one is geared towards batch manufacture and the other towards single wafer manufacture. The bash system can do 55 by 2 inch substrates or 3 by 8 inch substrates, and the single wafer is obviously for single wafer manufacture. Both systems are geared towards having very high etch rates, but also very serviceable in the sense that they've been designed for true production environments.